Hi, in this video we learn a new way of evaluating certain types of limits called L'Hôpital's rule. The name of this rule comes from the name of its publisher, le Marquis Guillaume de l'Hôpital, who published one of the first calculus textbooks in 1696, but it is believed to have been discovered by the famous Swiss mathematician Johann Bernoulli. Consider the following limit. The limit as x goes to 1 of sine of x minus 1 over e to the 2x minus 2, all that minus 1. Let f of x be the numerator, sine of x minus 1, and g of x the denominator, e to the 2x minus 2 minus 1. The numerator and the denominator are both continuous functions, and so is their ratio. We might therefore be tempted to simply substitute x by 1 to evaluate the limit, but if we do this, we run into a problem. F of 1 is sine of 0, which is 0, and g of 1 is e to the 0 minus 1, which is 1 minus 1, so overall 0 as well. We call this a limit of the form 0 over 0, the same type that we always get when evaluating derivatives using the limit definition. And as you now know, the form of this limit is indeterminate. We cannot tell from this whether it exists, and if it does, where it converges to. We've seen numerous tricks at the beginning of the semester to deal with limits of this form, such as factoring, multiplying, and dividing by the conjugate, or write the fraction as a simple fraction, but none of those really apply here. This video is about another trick that we can use that is extremely powerful. We will soon state what that trick is, but before that, we will use the given limit to illustrate why it works. The main idea is that the functions f and g are close to their linear approximations near x equals 1, and we could evaluate the limit of f of x over g of x by evaluating the limit of the ratio of their linear approximations L of f of x over L of g of x. To compute the linear approximations at x equals 1, we need the slopes of the tangent lines, and for this we need the derivatives of each function. We have that f prime is the derivative of sine of x minus 1, and using the chain rule, it is equal to cos of x minus 1 times the derivative of x minus 1, which is 1. Overall, it is cos of x minus 1. Therefore, f prime of 1 is cos of 1 minus 1, so cos of 0, which is 1. So f prime of 1 is 1. G prime of x is the derivative of e to the 2x minus 2 minus 1, and using the chain rule for the first term, we get e to the 2x minus 2 times 2 minus 0. At x equals 1, 2x minus 2 is equal to 0, and therefore g prime of 1 is 2 times e to the 0, which is 2 times 1, which is 2. So g prime of 1 is 2. The linear approximation for f is f of 1 plus f prime of 1 times x minus 1, and that's equal to 0 plus 1 times x minus 1, so x minus 1 overall. So remember, we use the fact that f of 1 is 0 and f prime of 1 is 1. The linear approximation for g is similarly g of 1 plus g prime of 1 times x minus 1, and we had seen that g of 1 was 0 and g prime of 1 was 2, so that's going to be equal to 0 plus 2 times x minus 1, so 2 times x minus 1. The following graph illustrates f in green and g in red. The dashed lines are the two linear approximations that are tangent to the functions at the point 1, 0, because both f of 1 and g of 1 are 0, so they're going both through the point 1, 0. We have also added the slope of each line. Since f prime of 1 is 1 and g prime of 1 is 2, then this explains why the dashed line in red is steeper than the dashed line in green. One has a slope of 1, the other has a slope of 2. Our main idea is to consider the ratio of the linear approximations as opposed to the ratio of the two functions. Doing this, we get rather than the limit of f over g, the limit of L of f of x over L of g of x, which is f of 1 plus f prime 1 x minus 1 over g of 1 plus g prime 1 x minus 1. And now realize that both f of 1 and g of 1 are 0 because the limit is of the form 0 over 0. And this is what we have tried to emphasize in red. By removing these two terms, because they're both 0, we come to realize that x minus 1 is a common factor in the numerator and the denominator. And we can simplify it and get simply a limit of f prime of 1 over g prime of 1. And those are both constants. So the limit of a constant being just the constant itself, the limit is just f prime of 1 over g prime of 1. Looking at the graph again, this means that the limit of f over g at x equals 1 is in this case the ratio of the slopes of the linear approximations, or equivalently the slopes of the tangent line. So this means that the limit of sine of x minus 1 over e to the 2x minus 2 minus 1 is 1 over 2. Because it's f prime of 1 over f g prime of 1. And that's equivalent to 1/2. To recap, we have calculated the limit as x approaches 1 of f of x over g of x, and have obtained f prime of 1 over g prime of 1. One last thing to notice is that if f prime and g prime are continuous, this would also be the limit of f prime of x over g prime of x. So looking at each limit at the extremities of the equation, we see that the limit of the ratio of f of x over g of x is equal to the limit of f prime x over g prime x. This is quite surprising. So the following result, which is a result published by Le Marquis de l'Hôpital, says that if f and g are functions that have continuous derivatives, then if the limit of f of x over g of x is of the form 0 over 0, or equivalently that g of a and f of a are both 0, then under the extra assumption that g prime of a is not 0, the limit of f of x over g of x is the limit of f prime x over g prime x. In the previous example, and using the graph of f, g, and their linear approximations, we have tried to explain why this result is valid. So to illustrate the result once more, consider the limit as x approaches 4 of square root of x minus 2 over x minus 4. When we replace x by 4, both the numerator and denominator evaluate to 0. So this is the limit of the form 0 over 0. At the beginning of the course, we have seen that we can evaluate such limit by multiplying and dividing by the conjugate of square root of x minus 2. But if we use L'Hôpital's rule instead, we obtain the limit of the ratio of the derivatives. The derivative of square root of x minus 2 is the derivative of x to the 1/2 minus 2, which gives 1/2 x to the minus 1/2 minus 0. The derivative of the denominator, x minus 4, is of course 1. So the limit is equivalent, according to L'Hôpital's rule, to the limit of 1/2 x to the minus 1/2 over 1. Notice how we have added the letter h above the equality sign to indicate that the rule was used. If we send x to the minus 1/2 to the denominator in order to change the negative power to a positive power, we get the limit of 1 over 2 square root of x. As x approaches 4, the expression approaches 1 over 2 times 2, so 1/4. L'Hôpital's rule works with limits of the form 0 over 0, but it works too with limits of the form plus or minus infinity over infinity. This is also an indeterminate form. With limits of the form infinity over infinity, we can pretty much obtain any value, and we cannot just say that the limit is 1. In general, it won't be. As an example, take the limit as x approaches infinity of e to the 3x over x squared. In the numerator, since 3x goes to infinity, the exponent goes to infinity, and e to the 3x goes to infinity as well. That is because the exponential function grows without bounds. So if the exponent gets large, then so does the function values. The denominator x squared goes to infinity as well when x goes to infinity. So overall, this is the limit of the form infinity over infinity, and we can apply L'Hôpital's rule. The limit is equal to the limit of the ratio of the derivatives, which are e to the 3x times 3, that's using the chain rule, over 2x, which is the derivative of x squared. Just make sure that you're not applying the quotient rule and differentiating the ratio, because that is not what L'Hôpital's rule says. We compute the derivatives of the numerator and the denominator and take their ratio. That is why we get e to the 3x times 3 over 2x. Now, as x approaches infinity, the numerator and the denominator are still approaching infinity. The limit is still of the form infinity over infinity, and we apply L'Hopital's rule once more. The derivative of the numerator is e to the 3x times 3 again, so times 3 squared. So note that this extra 3 comes from applying the chain rule a second time to e to the 3x. We divide this by the derivative of 2x, which is 2. So now overall we get the limit of 9 e to the 3x over 2. And it is not of the form infinity over infinity anymore. The numerator still goes to infinity, but the denominator now goes to 2, so the limit is infinity. Note finally that this limit would indicate that as x goes to infinity, so does the function e to the 3x over x squared. Thanks for watching.